So the empirical rule of normal distributions is quite informative in the sense oftentimes you don't even have to do a lot of analysis just by looking at a bell curve. You can get a quick idea about the probabilities. So bell curve definitely has to be like a bell. Hopefully. Not bad. I have to ignore that. I can't. Better. Better. Okay. So if the data has a bell curve histogram, so it follows a normal distribution, then from the mean, one standard deviation to the right, one standard deviation to the left. So what percent would lie, what percent of data would lie between those 2 points? It is 68%. Good.
Is it always 16?
Mm-hmm. Within 2 standard deviations from the mean, you will have 95% of the data. Good. Within 3 standard deviations from the mean, you will have 99.7% of the data. Does that make sense? It is given. These are golden numbers. So within 1 standard deviation, we would have 68%. Within 2 standard deviations, we will have 95%. Within 3 standard deviations, we will have 99.7%. Was Chebyshev right? He better be. Or it's kind of like reading this. Was he right? Yeah. Because he said, well, if you go to standard deviations on either side, you will have at least 75%. So for a normal distribution, it is 95%. Go ahead, pick up your calculator and plug in k equals 3 in that formula and tell me what that percent will be. So 88.9 within 3 standard deviations, and he said at least 88.9. I don't know why I put minus there. You can't do algebra. So we have 99.7%. These numbers will only work with a bell curve. If you have a skewed distribution, you can't use this. But will Chebyshev's theorem hold true? Yes, it will. Are we clear with this rule?
Yeah.
So the speeds for 8 vehicles are listed. 8, yes. Using the sample statistics from exercise 29, determine which of the data entries are unusual, are any of the data entries very unusual, explain your reasoning. We're now going to go back to problem 29. Pick up your calculator, plug those numbers in and tell me what the mean and standard deviation are. It's a good exercise. So what is the mean?
71.
The average or mean is 71. And what is the standard deviation?
7.19.
7.5.
19. 9.
1.19.
7.19.
They could call it 7.2.
Alright.
Doesn't matter. Now, when would we consider an observation to be unusual when it doesn't fit the profile? Do you agree? Yes? If an observation fell right over here, would you consider it to fit the profile?
Yes.
How about that?
Yes.
There,
Yes.
there,
Yes.
there,
Yes.
there.
No.
Okay. So if it falls past 3 standard deviations on the right hand side, or below 3 standard deviations on the left hand side, an observation would be unusual. So the question says which are unusual and which are very unusual. Typically, we look for 2 standard deviations. If an observation falls slightly outside 2 standard deviations, we call it unusual. But if it goes way past 3 standard deviations, it is very unusual. Does that make sense? So let's find 2 standard deviations from the mean and 3 standard deviations from the mean on either side. Do not just subtract 3 and add 3 to the mean. It is 3 standard deviations, so it has to be 3 times 7.19. Standard deviations that high. Okay. Two standard deviations to the right, 85.38.
It's,
Too high.
I got 8.4.
Fine.
Okay.
One more standard deviation, we just add 7.19 to it. It's 90, no,
0.57.
92.57. On this side, you have to subtract 2 standard deviations. What do we get? Over here.
No,
Wait, what? Shouldn't it be 49?
49.49.
Yeah.
49 point what?
430.
So the mean is 71, the standard deviation is 7.19, it's 35. Do you think any of the observations over there are very unusual?
No.
No, they're all.
None of them are, right? Every single observation up there falls within 95%. Right? If it falls within 95%, it is going to fall within 99.7%. So none of the observations up there are unusual. Does that make sense?
Yeah.
So you can only do this for normally distributed data, And naturally, the book is making the assumption that it is normally distributed. Are we clear?